Hello student, I am Dr. Ajay Kumar Sinha. Now today I will continue from the last class. Yesterday I have discussed about the ionization enthalpy. Then two more points, two few examples I want to give you because that is very important for examination point of view. Okay. Then that is related to boron and beryllium. Boron and beryllium. First ionization enthalpy of boron, that is Z is equal to 5, atomic number 5, 1s square, 2s square, 2p1 electronic configuration, and beryllium is 1 less, means 1s square, 2s square. Then first ionization enthalpy of boron is slightly less than that of beryllium, even though the former has a greater nuclear charge. Explanation for this I am telling you. When we consider the same principal quantum level, an S electron is attracted to nucleus more than a P electron. In beryllium has 4 electrons, 1s square, 2s square. Keep in mind. In beryllium, the electron removal during the ionization is an S electron, whereas the electron removed during the ionization of boron is a P electron. In beryllium, the electron removed during the ionization is an S electron, whereas the electron removed during ionization of boron is a P electron. The penetration of a 2s electron to the nucleus is more than that of a 2p electron. Hence, the 2p electron of boron is more shielded from the nucleus by a inner core of electron than the 2s electron of beryllium. This 2p electron of boron is more shielded from the nucleus by the inner core of electrons than the 2s electrons of beryllium. Therefore, it is easier to remove the 2p electrons from boron compared to the removal of a 2s electron from beryllium. Thus, boron has a smaller first ionization energy than beryllium. Question is asked. Now, another important thing, analogy, not an anomaly. What is that anomaly? Another I am talking about another anomaly is the smaller first ionization enthalpy of oxygen compared to nitrogen. Again, this question is asked. A smaller first ionization enthalpy of oxygen compared to nitrogen. Okay. Here what happens? This anomaly arises because in the nitrogen 7 electrons are there, 1s square, 2s square, 2p3. In p3 electrons are there, 1 in each px, py, pz. Then 3 2p electrons resides in different atomic orbitals according to Hund rule. Whereas in the oxygen is 8, 1 more than nitrogen. Then eighth electron is coming to the px, means in px 2 electron. After filling 1 1 1 in each px, py, pz, again it is coming to the first one px. Then only py and pz have 1 1 electron. Then where is in the oxygen atom? I told you only in oxygen atom, only now in P2 py, pz only they have 1 1 electron. Then 2 of 4 2p electrons must occupy the same 2p orbitals, resulting in an increased electron repulsion. Here I want to clear that because in the nitrogen atom 3 2p electrons reside in a different atomic orbitals, Hund's rule, according to the Hund's rule, whereas in the oxygen atom 2 of the 4 2p electrons must occupy the same 2p orbital, resulting in an increased electron repulsion. Consequently, it is easier to remove the fourth 2p orbitals from oxygen than it is to remove one of the 3 2p electron from nitrogen. Okay, this is the explanation. Now I am going to discuss electron gain enthalpy, fourth, that is the physical property. Electron gain enthalpy is also known as electron affinity. When an electron is added to a neutral gaseous atom like X, to convert it into a negative ion, means here it is the we will talk about the formation of anion. You know that in the formation of anion, electron is required from the outside. Then when an electron is added to a neutral gaseous atom like X, to convert it into a negative ion, the enthalpy change accompanying the process is defined as the electron gain enthalpy, that is the delta H. Delta H is the symbol for electron gain enthalpy. It is also called affinity. Affinity means affection for the electron. Again I am telling you, when electron is added to a neutral gaseous atom X, to convert it into a negative ion, the enthalpy change accompanying the process is defined as the electron gain enthalpy, that is denoted by delta H. Electron gain enthalpy provides a measure of the Eg with which an atom adds an electron to form an ion. Now I am telling you here, to gain the electron, two things is possible. Because name itself is affinity, electron affinity, or you can tell electron gain enthalpy. Then to get one electron, it can do things. It can do two things. First, it can lose the electron, or second, it can gain the electron. Both are possible because they have affinity for electron. They want electron. They have affection. For that, they can lose the electron. They can lose the energy, as well as they can take the energy also. These two things you keep in mind. Both is possible. Loss of heat or gain of heat. Okay, this is important, very very important here. Depending on the element, the process of adding an electron to the atom can be either endothermic or exothermic. Endothermic means gain of electron. When in a process heat is absorbed, that is called endothermic, and when heat is going outside, then it is called exothermic. Heat released, that is called exothermic, and delta is given the sign minus, means negative, and when heat is absorbed, that time it is given positive. Anyone you keep in mind, then you will not get confused. Negative means heat is releasing, going outside. Then positive means when it will absorb the heat, then delta H will be positive. When heat is absorbed, and delta H is equal to negative when heat is released. For many electrons, energy is released when an electron is added to the atom, and the electron gain enthalpy is negative. As for example, group 17 elements, means halogen group, have a very high negative electron gain enthalpies because they can attain a stable noble gas electronic configuration by picking up an electron. On the other hand, noble gases have large positive electron gain enthalpy. On the other hand, noble gases have large positive electron gain enthalpies because the electron has to enter the next higher principal quantum level, leading to very unstable electronic configuration. I told you that noble gases are stable because their outermost orbit is filled, but here in this case, if any electron is added to this is the 18th group are noble gases, then new orbit will be opened. That's why next higher principal quantum level will open, level will start or open, new orbit will open, leading to a very unstable electronic configuration. Here one should note, it may be noted that electron gain enthalpies have large negative values towards the upper right of the periodic table preceding to the noble gases. Before the noble gases, whoever you can say elements are there, for them its value will be more because they are very close to the stable configuration of noble gases. The variation in electron gain enthalpies of elements is less systematic than for ionization enthalpies. Variation of electron gain enthalpies of element is not very systematic, less systematic than for ionization enthalpies. As a general rule, electron gain enthalpy, that is the affinity, I am talking about the electron affinity, both are same. As a general rule, electron gain enthalpy becomes more negative with increase in the atomic number across a period. The electron nucleus charge increases from left to right across a period, and consequently it will be easier to add an electron to a smaller atom, since the added electron on an average would be closer to the positively charged ions, because positively charged ions will attract the outermost electron. That's why it is energy will increase. Its energy will increase, and that this thing. That's why energy will increase means delta H will be more negative. We should also now next things important point. We should also expect electron gain enthalpy to become less negative as we go down a group. Now we are discussing about the group. Here in group what will happen? There is a expectation. What expectation means? It will, not expectation, it will. Electron gain enthalpy that will here in the sense of delta H. What happened in period? Reverse cases in group. We should also expect electron gain enthalpy to become less negative as we go down a group, because the size of the atom increases and the added electron would be farther from the nucleus, far from the nucleus. This is generally the case. This is general case I have discussed now. However, electron gain enthalpy of oxygen and fluorine, question is asked that this things, electron gain enthalpy of oxygen or fluorine is less negative than that of succeeding element. Means you are talking about the this thing before oxygen. That is the 17, 16, 15 I am talking about. 15. This here I am talking about electron gain enthalpy of oxygen or fluorine is less negative than that of succeeding element like 14 and 15, 13, 14, 15. This is because when an electron is added to oxygen or fluorine, the added electron goes to the smaller means n is equal to 2 quantum level and suffers significant repulsion from the other electrons present in this level, because n is equal to 2, size is small. In that electrons are there, already electrons are there, and extra electron will enter there only, then repulsion will be there. Then due to this repulsion suffers significant due to this extra electron, significant repulsion from the other electrons happens there in that orbit. Now if size is big, means for n is equal to 3 quantum level, like sulfur or chlorine. Sulfur or chlorine means next to oxygen and fluorine, down sulfur and chlorine is there. Then here what happened? For the n is equal to 3 quantum level, S or Cl, the added electron occupies a larger region of space and the electron repulsion is much less, very less. Okay, this is the you can say explanation. Then if repulsion is less, then easily you can add the electron. Then this required energy will be less. Means not this energy released will be less. Delta H will be less negative. Now I am going to discuss another properties, that is the electronegativity But here in this only electron gain enthalpy, one advanced can say knowledge I want to tell you. That question may be asked for advanced IIT student. One relation is there. That relation just I am discussing, that in this delta H change means a change in enthalpy, change in can say electron gain enthalpy. Delta H has a relation with heat capacity and temperature. It has relation with heat capacity and temperature. That relation, what is that relation? I want to tell you. This is the mathematical, and this will be discussed at proper place. And when we will start thermodynamics, I think it is there, or equilibrium chapter, then this we will discuss. But this is this relation here I want to tell you. What is that relation? Then delta H at equilibrium. Delta H means change in enthalpy at equilibrium. Equilibrium chapter we will tell. Delta H at equilibrium is equal to minus delta A S, that is the minus delta minus A, right, minus A C. Here we are talking about the heat capacity. AC is representing here heat capacity. Then delta H is equal to minus delta A, down you write a small c, means heat capacity, minus 5/2 RT. This is a relation. This is the relation between heat capacity and enthalpy. Again I am telling you, delta H is equal to minus A, down a small c you can write with A, minus 5/2 RT. Then T is here temperature, or you can tell this has a relation. This electron gain enthalpy is also called electron affinity. Then electron affinity is defined as absolute zero, and therefore at any other temperature like T, heat capacity of the reactant and products have to be taken into account, in which it taken into account in equation. Which equation? Then delta H is equal to minus A C. AC means AC means heat capacity, minus 5/2 RT. Delta H is equal to minus A minus 5/2 RT. Now I am going to discuss electronegativity. This is very, very important. Electronegativity concept is very, very important. A qualitative measure of the ability of an atom in a chemical compound to attract shared electron to itself is called electronegativity. Here you should always keep in mind, electronegativity is related to a chemical compound. In chemical compound, maybe more than 2 atom, 3 atom, maybe 2 atom, 3 atom, 4 atom, like that way. Then in compound atoms are there. Then this atom, how much has attraction, how much it can attract the shared electrons to itself, then this property is called electronegativity. Then this is the ability of an atom in a chemical compound to attract shared electron to itself is called a electronegativity. Unlike ionization enthalpy, in ionization enthalpy, this is not the case. Unlike ionization enthalpy and electron gain enthalpy, this does not happen in these two cases. This electronegativity is not a measurable quantity. However, a number of numerical scales, this question is asked. It is not measurable quantity. Despite that, a number of numerical scales of electronegativity of elements has been created. What are that? Many scales are there. Then 2 scale, 3 scale I am telling you. Question is asked. First scale to measure this electronegativity, that is the Pauling scale first. Second, Mulliken-Jaffe scale, and third, Allred-Rocho scale. Three are there. Then out of these 3, Pauling scale is widely used, and because you have to know something about the electronegativity, how will you measure? Some idea should be there, how much they are attracting. Then Pauling scale is widely used. Linus Pauling, an American scientist, in 1922 assigned arbitrary, without any reason and rhyme, a value of 4.04, simply 4 you can tell, to fluorine. That is the highest electronegativity for the fluorine. Always question is asked that fluorine has highest electronegativity value, that is 4.0. This is very important things I told you. The element considered to have the greatest ability to attract electrons, and that is the fluorine. Approximate values for the electronegativity of few elements I will tell you. As for example, now electronegative value on Pauling scales, I am telling you, you should know from in period you can see from lithium to fluorine, period second, lithium to fluorine. Then lithium is only one value, 1.0, beryllium 1.5. Slowly it is increasing towards fluorine. Boron 2.0, carbon 2.5, nitrogen 3.0, oxygen 3.5, fluorine 4.0. Then before fluorine, oxygen is there, 3.5. Before oxygen, nitrogen is there, 3. Carbon, before nitrogen, carbon is there, 2.5. Then back it will come, it will decrease, and from lithium to fluorine, it will increase. And this for period third, again same way, sodium to chlorine. Sodium has only 0.9, magnesium 0.12, aluminum 1.5, silicon 1.8, phosphorus 2.5, sulfur 2.5, chlorine 3.0. And one more thing, this I have told about the variation in period. Like that way, in group, reverse case will be there. Electronegativity generally increases across a period from left to right. that is from lithium to fluorine, I have told you, and decreases down a group, say from fluorine to astatine. Means fluorine value is 4.0, chlorine 3.0, bromine 2.8, iodine 2.5, astatine 2.2. This is the case I have told in group. How can actually now these things are there? Other things, the attraction between the outer. Actually, how will you tell how radius and electronegativities are related? I am going to tell that things. Okay, then the attraction between the outermost orbit, outer electron in the outermost orbit or valence electron, you can tell. The attraction between the outer or valence electron, you can tell, and the nucleus increases as the atomic radius decreases in a period. This very, very important thing, how radius and electronegativities are related, I am telling you. The attraction between the valence electron, means outermost, and the nucleus increases as the atomic radius decreases in a period. That already I have discussed. The electronegativity also increases. Just same way here, the electronegativity also increases. On the same account, electronegativity values decreases with increase in atomic radii down a group. What will happen in period? Reverse will be in the case of group. Then on the same account, electronegativity value decreases with the increase in atomic radii down a group. The trend is similar to that of ionization enthalpy. Both are same type of trend. Knowing the relationship between electronegativity and atomic radius, you can tell actually so many things. Now I am means you can tell about the these things about the metal and non-metal property. You can have idea. Now I am telling you further, non-metallic elements have a strong tendency to gain electrons. Again, very, very out of metal and non-metal, if you compare metal and non-metal, then non-metallic elements, means P block elements, non-metallic elements have a strong tendency to gain electrons. Therefore, electronegativity is directly related to the non-metallic property of elements. It can be further extended to say that electronegativity is inversely related to the metallic property. Reverse case. In case of metal, it is inversely. Means electronegativity is inversely related to the metallic properties of the elements. Thus, the increase in electronegativity across a period is accompanied by an increase in non-metallic properties or decrease in metallic properties. If non-metallic property is increasing, then automatically metallic properties will decrease. Metallic properties of electron will decrease. Similarly, here in group, the decrease in electronegativity down a group is accompanied by a decrease in non-metallic properties or increase in metallic properties of elements. This I have discussed about today I have discussed about the two properties, that is the electron gain enthalpy, also called electron affinity, and second things I discussed electronegativity of an atom in a chemical compound. Here I will some diagram I will send it, then you can understand why this also. Then now today I am stopping only here. Next class I will start with chemical properties. Thank you.